so it's my honor to introduce him. So Anthony comes to us from southern suburb of Chicago, White Sox country. I met him as a freshman. I teach the organic chemistry classes here, typically for sophomores. Anthony came in and asked me, hey, can I take your class as a freshman? I said no. He said, come on. I thought that was a pretty good argument, so I let him take it. Usually that doesn't work out. In this case, it worked out very well, and he stayed with us and took a lot more chemistry with us. He then worked in my lab last summer on the synthetic project that you're going to hear about today. If you haven't heard a sort of synthesis talk, I think there's two ways to come at this. One is that there is a point to all this. There's 2 points, really. One is that we need new molecules for drugs. No one thinks that we have the perfect drugs out there yet. And so being able to make new things opens the playing field, opens this open space that we can get stuff. But also, there's an intrinsic creativity to this work, right? So we are only kind of bounded by our imagination and what we can think about. And so a lot of this work is trying to say, what could we make? Is this a cool way to do things? And so I think that he really brought some creativity and problem solving to this process. So feel free to ask him any questions afterwards, including how many bonds carbon takes. And again, after this, he is going to do postgraduate work with the Seattle Mariners. I'm sure that they have lots of, again, interesting questions that chemists like ourselves are trained to solve. So without further ado.
All right, thank you, Professor Deverich, for that wonderful introduction. Like he said, I had the honor and pleasure of doing research with him this past summer. And I know some of you guys have basketball tournaments to get to, other of us have happy hours to get to, so we'll get right into this. Like he said, we're going to be looking at the synthesis and trapping studies of Thienonaphthalene biradicals. Don't be too scared by the words that you may or may not understand. One, I don't completely understand them yet, and two, we're going to kind of do our best to break them down as we go along. But first, I kind of want to give a little bit of organic chemistry background here, so we're kind of all on the same page. So this, we're going to see a lot of lines and sticks. They are not stick figures, but they are carbon chains. And this kind of carbon chain will correspond to what you see here. So this atom here is just a carbon atom bound to 3 hydrogens, and then we have a carbon atom double bonded to a different one, and then those 3 lines will represent a triple bond. And one thing to note here, carbon takes 4 bonds. That's one of the first things that Professor Deverich will tell you in organic. And if you take a look here, this carbon bound to 3 hydrogens, and then 1 carbon, 3 plus 1, you guessed it, 4. And then this carbon here will have the triple bond, and then that single bond, again, 4 bonds. Another compound that we'll kind of see come up again and again throughout this presentation is what's known as a benzene ring. And again, drawing in those atoms there, we'll see that each of those carbons will have a double bond and then bound to another carbon and a corresponding hydrogen atom bound to it as well. So now on to a couple of terms, symbols, and abbreviations for those terms. The first of which is Theophine, which is just an aromatic ring with a sulfur in it. Again, not shown, but looks like my laser's almost died. Again, not shown, but these are carbon atoms there. And then that's just the nomenclature for that is a Theophine ring. And then the next one we'll take a look at is Naphthalene. Naphthalene is simply, if you remember from the previous slide, we had that one benzene ring. Naphthalene is just 2 benzene rings fused together. And then we have a phenyl group, which is, again, just a benzene ring, but because chemists are lazy, they don't want to draw those in all the time, so they'll just denote it with a pH. And then we have a radical, which is a free or unbound electron, and that'll be denoted by a single dot, either above, below, or adjacent to whatever atom that radical happens to be located on. And then, just to kind of try and tie it back to those weird words at the end of the title slide, we have that Theophine ring, which kind of corresponds to the Thieno part, naphthalene, which corresponds to naphthalene part, and then we have biradicals, and there we have it, the radicals. So now we're kind of introduced to all of that weird chemistry jargon that you may have not been too familiar with. Now, before we go on to what we actually did in the backbone of our research, these are a couple of drugs that are commonly used and prescribed in the United States. And one thing to note is that they all have some kind of ring system. And more specifically, they all have a bicyclic ring system. And this is very prevalent, and bicyclic ring systems are used very frequently in biomedicinal chemistry due to their stability and versatility. And what I mean by versatility is that you can imagine adding different groups or different atoms, different functional groups onto each of these carbon atoms, and then therefore those different functional groups on different positions will yield different chemical properties and different biochemical properties within the body. And now to kind of tie it back to the real world, and by real world I mean money, these are the sales as of 2017 in US dollars of these drugs. And as you can see, these are not small numbers here. And then just to kind of show the growth and the size of the drug market, and introducing new potential drugs to that drug market is imperative to that growth. So now into what we actually did. So the backbone of our research came out of a paper from the National Laboratory of Applied Organic Chemistry at Lanzhou University in China. And what they did was they developed different routes of synthesis to conjugated enediens. And what those aren't super important, but what is important is that on their journey to synthesize those conjugated enediens, they had an intermediate step that interested us. And that was this step here. Before we kind of talk about why this was so interesting, we'll talk about what we're going to refer to these compounds as. So this one on the left, we will refer to as a dipropargyl sulfide. That sulfide coming from that sulfur atom. Propargyl, the way the carbon bonds are bound with that triple bond carbon in the middle of it, is kind of the nomenclature for that is propargyl, and then di, of course, because there are two. So there we have a dipropargyl sulfide, and on the right we have a biradical sulfone, that sulfone coming from the sulfur dioxide group, and the biradicals, of course, coming from those two radical-free unbound electrons. So, why were we interested in this step? Well, we wanted to see if we could trap these biradicals, and if we could trap them, we could create another cycle and create that bicyclic ring system. Again, that bicyclic ring system, big in biomedicinal chemistry and drug development. And how that would look is like this. We would try and somehow introduce sulfur dioxide into the system, have this second ring cyclize, and create that bicyclic ring compound. We'll get into the mechanism of how we did that, how we tried to do that in a few slides here. But first, kind of trying to tie it again back to those confusing words. Here we have that Theophine ring, and we have our biradicals, and we're almost there, almost to the Thienonaphthalene biradical whole little title part there. So, now what we actually did. So first, this was my first research position. So what I had to do was kind of get my feet wet in synthetic chemistry. So we took literature reactions, reactions that we knew would work, reactions that we had procedures for, and tried to recreate them, not just for the sake of recreating them, but also because we needed them to synthesize our target compound. So the first of which, we took propargyl alcohol. Again, we have that propargyl group here, and that OH, the nomenclature for that OH is just alcohol. And then reacting that with specifically carbon tetrabromide, and that bromide ion will just pretty much kick off that alcohol and then replace it there as you see. Now what we do with that propargyl bromide is reacted with sodium sulfide, and that sodium sulfide atom will kind of kick off that bromide, and you can imagine that happening with two branches. So here we have our dipropargyl sulfide. Then we can take that dipropargyl sulfide, react it with oxone, that sulfur atom will be oxidized twice, and we'll have our dipropargyl sulfone. This next part, this next reaction, the mechanism is a little trickier, so I'm going to try and break it down step by step here. So then what we did was we reacted this diprobargyl sulfone with a base. We actually, for the synthetic chemists in the room, we used DABCO, but what that isn't super important. Point is, it's a very nucleophilic base. So this base has lone pairs, has a lone pair of electrons, and it'll pretty much snatch up that H, that hydrogen, if you will, from this carbon atom here, and create what's called a carboanion. And that carboanion is a negatively charged carbon atom. Again, now this carbon has 3 bonds. Like we said, carbon likes to take 4 bonds, so it'll try and rearrange itself so that it can have 4 bonds again. So these electrons will be on the move. They'll move over to this bond, creating a double bond. Then we'll have the electrons from this triple bond move over to this carbon atom, creating another carboanion, and in the process creating another double bond, but again, only 3 bonds. So these lone pair of electrons will pretty much snatch up that hydrogen that we have floating around with that base to add that H over here. So pretty much what we did is we just moved this H over here through using that base. And then you can imagine that happening on that bottom branch as well to give us those 2 double bonds. So after that, we'll have something called Garrett-Braverman cyclization, which is from a paper that we utilize a little bit, mostly just to understand this mechanism. And what happens here is, again, it's pretty much just an arrangement of electrons. An electron from this double bond will move over here along with this one to kind of close this and create that bond. And another electron will move to this carbon here to create that radical, and it'll happen again on the bottom there. So, and then really quickly, before we show how this cyclization finishes, I'd like to point out these 2 atoms, or these 2 compounds are the same. I just changed a couple things around for the visualization of the next step here. So this pH up here corresponds with this one here. Like I said, that pH just denotes that ring. And then this pH again is still just this pH, and then we still have those radicals present. So what happens now is that these radicals just kind of move around to create that bond here. A few other things happen, but that's pretty much the gist. And then we have this 3-membered ring system here on the right. So you'll notice that this says fast and this says slow. So what that pretty much means is this is in constant equilibrium. So it's either like this or we have those free radicals. But more often than not, we'll find it like this because this is a lot more stable. Free radicals, very unstable, highly reactive, so we won't find it in this conformation too often. And that's something to keep in mind as we go on here. Like I said, we're trying to trap those biradicals. So trapping those when most of the time it's in this might be a little difficult. Again, just to kind of tie it back to those weird couple words, so now we have our Theophine, our naphthalene, and our biradicals, and that's how we get that Thienonaphthalene biradicals. So, back to trapping the biradical and how we're going to actually try and do it. This is the novel idea that we have, trying to make this new compound. So what we tried to do is we tried to introduce sulfur dioxide to the system via DABSO, which for the synthetic chemists is just DABCO with a sulfur dioxide group bonded to either of the nitrogens. But the important thing to note is that we have sulfur dioxide, introducing it, and we're trying to have the lone pair electrons of that sulfur dioxide pretty much bind to these radicals and trap them so that we get this biradical system, or this bicyclic system. And what we want, and if we do this, what's nice about using sulfur dioxide is that sulfur dioxide is a good leaving group. And what that means is it's very stable on its own. So if we get this, we can pretty much kick this off whenever we need to access this biradical again. So, before we get into if it worked or how it worked or what have you, we had to see what we actually had after all of these reactions. And first, what we used to characterize or identify what we had was GCMS, or gas chromatography mass spectrometry. I understand most of you probably don't know what that is, so we're going to try and get everyone on the same page here with a little GCMS overview. So first things first, you inject your sample into some injector port, and that ejector port is extremely hot, causing your sample to go to the gas phase. There's the gas part of GCMS. And then as you inject it, it enters a column, and in that column, the components of your sample get separated based on a variety of different chemical properties. The GCMS uses polarity to separate it, and as those eluents, or as those components elute from the column, they'll elute at a specific time, and then that time that those components elute is called the retention time of the component. And then you can, that will yield, that elutant will yield some kind of signal, and you can plot that signal against the time, its retention time, that it exits the column. And just as a little visualization, this is actually a different kind of separation, but the visualization is pretty similar. Like I said, our GCMS uses polarity. This is actually a size exclusion chromatography. So as you can see here, here's our sample with a whole bunch of different components. As we move on, it kind of starts to separate, and by the end, we have them separated by size. Like I said, it will be the same principle, except in the GCMS, the instruments that we use, it'll be separated by polarity. So those different components will exit the column by their polarity rather than their size. So now on to using the GCMS to help us identify what we had. Unfortunately, we had a little bit of a problem identifying these compounds using the GCMS. So first what we did is we ran our starting material, our dipropargyl sulfone, through the GCMS, and it yielded this plot here, not super important on its own. And then we ran the 3-membered ring system, so this was the dipropargyl sulfone with that base. So no sulfur dioxide yet, not trying to trap those biradicals quite yet. Again, not too impressive on its own, but one thing to note is these look pretty similar. And then we ran it again with the dipropargyl sulfone reacted with that SO2, so trying to trap those radicals. And again, it looked very similar. So really the important thing here is that these all look the same. So we couldn't really get too much useful information from them. And the fact that this last one looked the same as our first one, not super concerning, not super surprising, because like I said, this is kind of our whole novel idea here. This is the new compound we're trying to make. So the fact that maybe it didn't work, not shocking. But the fact that we don't see a difference between these two was worrisome, because this is a literature reaction. Adding this with base, that was a literature reaction, so we should see some kind of difference there. So rather than just giving up, which I'm sure Professor Deverett wouldn't have let me do anyway, we went to a different detection and identification instrument, the NMR, or nuclear magnetic resonance. And again, I'm going to try and give a brief overview here so we can all get on the same page. This instrument, super complicated, so don't be upset, Professor Fleshman, with how I explain it here. Gonna try and keep it super basic. So each nucleus has some spin associated with it, and that spin generates a magnetic field, and that magnetic field is random. Okay, but something interesting happens when you apply an external magnetic field that's fixed. So when you apply some fixed external magnetic field, it either align the nucleus with or against the external magnet. And just a little visual on that. So here on the left we have those nucleus, we have the random magnetic fields, and then we apply some fixed magnetic field denoted H0. And now we have on the right our nuclei with either aligned with or against that magnetic field. And so like I said, you kind of shoot this magnetic field at your sample, and then you can read the difference of the magnetic field as it's exiting, as it finishes going through the sample, and that difference can yield different properties, chemical properties, specifically properties relating to the chemical structure of your sample. So that in mind, here are some NMR spectra. Again, up top here we have our dipropargyl sulfone. Excuse me. This spectra here is our 3-membered ring system. Again, we have literature spectra for both of these because they're known reactions. We have literature spectra, so we can match them to the spectra presented in that paper that we were working off of, and sure enough, they were a match. They looked like the spectra. We determined, okay, cool, our reactions did work. And one thing to note, couple peaks to note specifically, are the presence of this peak here a little after 4.5 and 5, and the presence a little after 7.5 for this 3-membered ring system, and the absence of them on this dipropargyl sulfone. What we determined was that those peaks are characteristic of that Theophine ring, and so the presence of those would be imperative to concluding if we had that bicyclic ring system, because again, that bicyclic ring system has that Theophine ring as well. So now on to our target molecule, the spectra for our target molecule. As you may note, we do not have those rings present here. Again, this spectra is just the dipropargyl sulfone, our starting material, but unfortunately we did not see those rings present, which led us to conclude that we did not, in fact, have our target molecule. We were not able to synthesize it, and a further conclusion that we drew was that we actually just had this dipropargyl sulfone, and we had no reaction, so we pretty much just had starting material. Again, this peak here corresponds to this peak. These two peaks correspond to each other. This peak, I believe we just wrote off to solvent and other reagent garbage. And then we have this big peak here. You can kind of see it peeking out here, just a little less intense. And then so we kind of just determined that we had no reaction and we just had that starting material in our sample. So that solves the problem of what we had, but it doesn't solve the problem of why the GCMS didn't work. So going back to the GCMS spectra, what we concluded is that we actually have both our starting material and that 3-membered ring system. So we concluded that our starting material actually corresponds to these little peaks here, and our 3-membered ring system corresponds to these large peaks. And remember back to the little GCMS overview, that injector port is very hot. So whatever is going through here is very hot, and we concluded that due to the heat, this dipropargyl sulfone will kind of cyclize on its own, and so that's why we see this in every spectra, or even the spectra without the base reaction happening. So unfortunately, we were not able to synthesize our target molecule. But there are a couple different ways that we can try and do so, one of which being a different method of introducing sulfur dioxide. Like I said, we used DAB-SO, which is a solid sulfur dioxide. We can try using gas or liquid, which are a lot harder to work with, which is kind of why we started with solid. But trying a different method of introducing sulfur dioxide might yield more success. And another thing to try is slowing down that initial radical reaction, that cyclization of that radical. And what might be a possible way to do that is by using a different branch atom or branch group here, rather than sulfur dioxide, using an oxygen or a sulfur atom, in hopes because we think that the cyclization of that radical is actually a product of the acidity of this hydrogen, and so changing that oxygen or sulfur could possibly change it, or will change the acidity and possibly change that rate of how quickly that cyclizes. So before we kind of get out of here, I'd like to thank a few people, one of which being the WISCamp group, which provided the funding for my research grant, and next Professor Debert for taking me in. I didn't have anything going for me that summer, and he kind of took me in and let me work in his lab. And then Professors David Hall, who had to take off, and Graham Sazma, who gave me feedback on my presentation, and Professor Graham was here all summer too, so he helped me out as well. And then DMART for always getting me what I needed out of the stock room, even if it was just beakers, because I was too lazy to do my dishes. And of course, Lawrence University. So with that, thank you very much for coming, and any questions?
Any you go back to the last GCMS slide?
Yeah.
So you said the injector port, concluded that the injector port was hot enough to auto cycle
Yeah.
size, whatever. Did you test out that theory?
We didn't. That was just kind of something we're like, that's the theory we're rolling with.
And then
So how would you test it? What would you do?
Damn, killing me here. Well, let's see. I always love Professor Dever to ask me those kind of questions.
If the hot thing is causing it?
Oh, you just do it without hot, yeah, lower the
Maybe
temperature, I
that's
guess.
hot, yeah.
and then what's the thermal? Do you know the thermal decomposition temperature of your starting material?
I do not know. Zach?
So you said there's different ways to introduce the sulfur.
Yeah.
Is that like doing a different like spectroscopy or NMR, or are there other different spectroscopies that you can use?
Yeah, so what I mean by introducing the sulfur dioxide is actually way back here. Okay, so this is where we introduce the sulfur dioxide to the reaction, and that doesn't really have anything to do with the detection of it. That's just using a different reagent. So we used a solid called DABSO, which again isn't too important, but you could try and introduce it using liquid sulfur dioxide or working in the gas phase and introducing that reagent in the gas phase.
So is there a different like spectroscopy you could use for like detection, or?
Well, there is different spectroscopy we can use, but that wasn't really the problem when introducing sulfur dioxide, if that makes sense.
Because I don't know if the detection was the problem there or not, or
Yeah.
it was just the sulfur.
Right, yeah, this kind of comes like pre-detection, if that makes sense. This is part of the reaction, and then we kind of test if it's actually there.
It's a good question. So the GCMS turns out to be a bad way to detect this, but some of the other ways, like the NMR, should have been a pretty decent way to detect it.
Actually, that leads into my question. I was curious if you could use the EPR to measure before you put the SO2, and if you do sort of like in situ measurement along with the EPR to monitor those radicals.
Yeah, I'm gonna be honest, I don't know much about the EPR.
Yeah, I mean, you can use EPR to look at unpaired electrons.
Yeah.
Essentially, so it depends on how long-lived that species is and whether you could see the electrons before you trap them.
But I assume that reaction is pretty darn fast, so you wouldn't be able to.
Yeah, well,
so if the SO2 is present, then it would be way too quick.
Yeah, I think what would be the problem is, I don't know, the speed of this reaction here, right? Because then if this goes to here really quickly, then we won't be able to see that.
So that leads to my question, which is, don't you need a base to form the ketene, what is that called? Alene?
Yeah.
The alene above? You need a base to form that, right?
Yes, that is
The
what-
green guy?
Yeah.
So, were you just assuming that the DABCO piece of the DABSO reagent was going to act as a base and introduce SO2, or did you have a base along with it when you tried the SO2?
No, we assumed that it would do both.
What is DAB? Can you say it one more time? And what is it?
DABCO.
DAB, what is it?
It's a base. I think I can draw it.
Is that a
Yes.
big name?
Do it.
Do you?
Yeah, it's like, oh my gosh, I really don't remember what it's called. All right.
I don't
here
even
we
know
go.
what it's called, so you're ahead of me.
All right, so there's, oh man, this is gonna be really hard. Okay, I think it's like something like that. All right, oh man.
Yeah. 600 ring.
You can just say, you don't.
No, you
I don't know what it's called though.
600 ring, and then you draw, there's a two carbon bridge.
So here, there's a bridge.
There's a two carbon bridge between, the nitrogens are connected by two carbons like 3 times.
Oh, so it's here and then, oh, oops, that looks over.
So like the one question you probably thought you wouldn't get.
Maybe
I'm so
here.
sorry.
2 carbons.
2 more carbons.
So in the back, 2 more carbons?
Yep. Yes.
1, 2.
Yes.
Sure.
Yep.
Yeah, there we go. And then the DABSO that we used to introduce sulfur dioxide just had a SO2 here and an SO2 here.
So what was your question again?
So my question was essentially, if you're waiting to form the biradical to take out one of the SO2s, then you don't have any base to form the dialene. So you never form any biradical and you never grab onto any of the SO2s. So you could maybe just add a little extra base on top of it and see if that initiated the reaction. I have another question for you. It's an annoying question because it's about your intro stuff, which is not your research. Why is Aleve so much less money than all those other drugs
Well,
that
the
you chose?
psychotic one
Well,
was.
Yeah,
Well, it's
The
because
antipsychotics.
these are all,
you got this one. This is the,
these are all, this is like over the counter, these are all prescription, I think, and they're all like named,
So
they're all like,
it's patents?
yeah.
Oh,
patents.
man, that's crazy.
Yeah,
That's a lot.
what's crazy is that's still so high,
yeah,
right?
because there's so many substitutes.
Yeah.
These are, and then again, these are actually top 10 commonly used and top 10 prescribed, so like if you, that's another reason why those are so.
Well, and naproxen's a highly prescribed anti-inflammatory as well, right? So it's also an anti-inflammatory.
Yeah, that's true.
Are there any more questions for Anthony? Okay, let's take it one more time.